All right, folks. Friday for us. Just another quick set of problems. I shouldn't say problems. Problem. Basically, just got a pushing problem for you, just so that you can now start to see how these problems start to evolve from what we've been doing this week into what we'll do next week. Right. So it is a good problem. It will get you started on section two homework and be able to help you get through at least the first couple of them. So, okay. So here we go. So yesterday, this was one of my key pieces that I wanted you to look at. So again, I just want to talk you through it. Our big thing that we're going to look for here is, do we have an applied force? And again, we're always going to have a friction. So I'm going to get rid of this here like this. Yeah. Do we have an applied force? When we have no applied force, that's our fun equals our negative force of friction. So remember, for that one, that's sliding, that's when we're decelerating, okay? When you're slowing down and stuff like that. Applied force means that fun equals our force applied minus our force of friction here, right? So that becomes an important one for us because we've used ones like this. So when we accelerate, when we push, now the difference for us is we may give you a force of friction or something along those lines, right? No unbalanced forces means our force applied is equal to our force of friction. Are we just barely getting it started to move? Because then this is the case. Or are we moving it at a constant rate of speed, right? No acceleration, then this is also that case as well, okay? So those become kind of what we look for and what we want to see out of these types of problems, okay? So a stick person pushes with an 85 Newton force, which causes the 125 kilogram box to move forward at a constant speed. Determine the coefficient of friction for the floor. Okay, so okay. So what we see here is we see that we've got a 85 Newton force, right? So that's gonna be part of it. We've got 125 kilogram mass, and then we're moving at a constant speed. So our mass is 125. Now, because the person pushes, right, with this 85 Newton force, that means that that's an applied force for them, okay? So that becomes our applied force. So that sets in a whole bunch of different options for us, right? At constant speed, so the velocity of our box is going to be constant, right? We want to find our kinetic coefficient of friction, right? So when we start to look at this, our fun is going to be zero, right? Because we're going at a constant speed, remember that means no acceleration. It's just like when we talk about barely getting an object to move. When we barely get an object to move, that means its fun is also zero. So because of that, we can look and say, all right, this point right here on our equation is going to be zero. We already know from the given information that our applied is an 85 Newton force, all right? So in order to solve for our force of friction, we'll just add it over to the other side. So at that point, we see our force of friction is 85 newtons, okay? So that was the first big step in order for us to be able to find the kinetic friction, okay? By us finding the force of friction now, what we can do is we can start to work with it. So knowing that our force of friction is 85 newtons, we can plug that into our mu of kinetic friction, mg cosine of theta. Again, here, the beautiful thing about these, you can assume that this angle here is likely zero unless it's actually explicitly stated in the problem. So when it becomes zero, that's beautiful because that means that the cosine is 1. Okay? So we have the 125 times the 9.8. So when we multiply those two together, we get 1,225. So to solve for our kinetic friction here, we take 85 divided by 1,225, and we find that the floor has a coefficient of kinetic friction of 0.069. Again, notice no label on the back end of this. The reason for that, this newtons and this newtons are getting canceled out, right? Because one's on top, one's on bottom. Those two are going to go bye-bye, leaving us with a labelless value. Okay? You'll find that I think the The third and fourth problem on the practice are a little bit tricky just because we have to use kinematics, but otherwise you should be able to do a bunch of those early starting problems. Okay. That's all I got for you for today. Take some time, work through some of those problems just so you get a little bit of a head start on next week. All right. Take care.